static stability and dynamic stability. That the aircraft has to return to its unperturbed condition. Dynamic stability tells us the aircraft will return to its previous condition following a perturbation. Okay, so static stability is the tendency that the aircraft has, while dynamic stability tells us if the aircraft returns to its unperturbed position. There are three types of stability. You can have a stable configuration, an unstable configuration, or a neutral configuration. What does this mean? In the case of a stable configuration, it means that if the aircraft experiences a disturbance, so a change in its dynamic characteristics, the aircraft will tend to return to its original state. Okay, so this is a stable configuration. Then we have an unstable configuration. That is, following a disturbance, the aircraft will move further away from the equilibrium point. And then we have the case of neutral stability. That is, following a perturbation, the aircraft will settle at a new stable configuration, which is different from the one it had before. So to illustrate this with an easy to visualize example, you can imagine the following three situations. Okay, you have a ball on a flat surface in a bowl on top of an upturned bowl, and you give it a small push. And what happens following the push? In this case, if this is our equilibrium condition, the ball will move further away. Okay? It will not be in equilibrium anymore. So this configuration is unstable. Okay? In this case, if we flick the ball, it will go up and then fall back down and resettle at the trim condition, at the stable condition. So this configuration is stable. In this case here, we flick it, the ball moves, and after a while it will stop at a different position, but it will stop. Okay, so this here is neutral. Okay, so these are the three types of stability that we can have. So three types of configuration. Stable, unstable, and neutral. The configuration is characterized, or how the aircraft reacts to a perturbation is characterized in terms of damping and frequency. And this tells us how quickly or how slowly the aircraft is going to converge to the equilibrium position, or how quickly or how slowly it is going to diverge from So we can have behaviors that are highly damped. That is the case, the bottom two graphs, where there is a very short period for which the aircraft, or in this case is the pitch attitudes, tends to the equilibrium condition. So there is no oscillation of the motion. So it follows almost an exponential decay or increase. And then we can have cases where you have a lot of oscillations. The two graphs on the left-hand side. So in this case, the perturbation is lightly damped. It means that it takes a lot of time for that particular state variable, again, the pitch attitude, to go back to its nominal value. Okay. So the behavior that a state variable has following a perturbation is either oscillating, so it will be a sine or cosine wave, or it will be an exponential, either an exponential that increases or an exponential that decreases. Okay, so this here will be stable. This curve here will be unstable. And the same can be said for oscillating behavior. Have something like this, which will be stable. Or something like this, which will be unstable. Okay. Everything clear? Yes? Okay. So we mentioned yesterday that, no, not yesterday, so Tuesday, when we were looking at the aerodynamic coefficients, that an aerodynamic coefficient has to be negative to contribute to the stability of the aircraft. The only case where this is not true is for the yaw moment due to side slip. So for this coefficient here, it contributes to stability only when positive. Okay? All the other cases, the aerodynamic coefficient has to be negative to contribute to the stability of the aircraft. Okay? Apart from this case. So when we did the worked example in class, we saw that we derived CL alpha and CL cube. Okay? And these have to both be negative to support, to help with the stability of the aircraft. In the tutorial, that you're going to do next week, you will have, I think it's the roll moments. You will derive the always have to be negative to support, to help with stability. So the only case is this one here, for which it is positive. Okay? Now, when looking at the stability of an aircraft, we can identify different modes, and this determines the direction of where the stability is looked at, addressed. So we have the case of longitudinal stability, which is in the pitch disturbance. And then we have lateral and directional modes for disturbances in yaw and roll. How the aircraft responds to a perturbation, which can be a gust, a change in the velocity of the air, change in pressure, and so on, will determine what type of response the aircraft has to the perturbation. So in the case of longitudinal stability, which is what happens to the aircraft when it is moving in this direction and it experiences a change in pitch, altitude, pitch angle. And there are two responses that the aircraft can have. One is the short pitch moment, and the other is the fugoid. So, in the case of longitudinal stability, longitudinal modes, we have short period, and we have fugoid. Okay. Now, what are the characteristics of these two modes? The characteristic of a short period pitch oscillation is that it is a very transient perturbation. As you can see from the top graph, the disturbances are quickly eliminated by the aircraft. So the aircraft returns in the case of 5-10 seconds to the equilibrium position. Okay, so short period mode is a heavily damped mode, and it's a perturbation that the aircraft can quickly recover from. That's not the case for a fugoid. A fugoid, you have a very slow decay rate of the oscillation, and you have a motion of the aircraft that goes continuously up and down. Now, the interesting thing is that the aircraft maintains an almost constant angle of attack, but it changes. There is an exchange between kinetic energy and potential energy. So as the aircraft is moving upwards, it will move at a lower speed. It will be going at a lower speed, and it will increase its potential energy. And then when it goes back down, the velocity increases and the altitude decreases. So you can see here that the speed has a military mode, while the red, which is the angle of attack, is almost constant around 0. Okay, so angle of attack in the case of a phugoid remains almost constant, but velocity oscillates quite substantially. Now these are some videos that hopefully, this is the short period mode. And this here is
Phugoid.
seafoam.
What's that?
Where are the pilots here? Did you do this? No. Sorry? No, of course. You don't want to have this effect, but when you are doing training or whatever, would you do this? Yes. Okay, so these are the two types of perturbations, sorry, the two modes that an aircraft can encounter when going through a disturbance in pitch. Okay?
Just first one short period, man. Still go into oscillation. Yeah, smaller.
Now, in the case of lateral and directional mobility, we have three types of possible modes. Two that are exponential, and one that is sinusoidal behavior. The modes are a roll mode, then we have a Dutch roll, and then we have a spiral. Okay. So the spiral and the roll mode are exponential in their behavior. And the roll mode is usually heavily damped by the aircraft. So the aircraft oscillates around the x-axis. So these are the wings, oscillates like this. Okay. But it is a quickly damped motion, so it's a very short-term perturbation that the aircraft quickly gets out of. In the case of the spiral, this can be either stable or unstable. So in the graph there, you have the case of a stable spiral. it is often unstable. And this can be very, very dangerous because particularly when the pilot does not have any visual clues. Because it's a perturbation that takes time to evolve, there isn't an immediate visual cue that you can rely upon to notice that the state vectors of the aircraft are changing rapidly. So a pilot, particularly with lack of visibility, could enter an unstable spiral mode, which could be very dangerous for the aircraft. And then we have the case of the Dutch roll. The Dutch roll is a perturbation which doesn't act along one axis, but combines perturbations around the x-axis, so a rolling mode, as well as a perturbation around the z-axis, that is a yaw mode. So there is a combination of perturbation in the around the z-axis, so the aircraft moves in this direction, and around the x-axis, so the aircraft moves in this direction as well. So there is the superimposition of two perturbations in the case of the Dutch roll. Oscillations around the x-axis that gives rise to a rolling motion, and then oscillations around the z-axis that give rise to a yawing motion. The Dutch roll, as you can see in the picture, is lightly damped, and it is a type of perturbation that is very uncomfortable for the pilot and even more so for the passengers. So I'll show you a video of the Dutch roll.
Unless you can fly, not bad. Trong luôn, the upwind, downwind.
X-axis, so rolling, but also moving around the z-axis.
那个 upwind 就是 headwind，
这个不是他们会从上面上，没有这样的。
And this here is the case of a spiral. A spiral mode, which, as the name suggests, if you are looking at the trajectory of the aircraft is moving in this direction, you tend to Dutch roll and spiral. No. Did you enjoy the Dutch roll? No. Okay. Okay.
This chapter like quite relaxed now.
Yeah, exactly. It's never relaxed.
Oh, so fast forward now. Sekali. They're working like that only. They'll come out could be
Stability,
died.
short period. Okay. Short period is a disturbance in pitch. So around the y-axis. Okay. It causes the aircraft to change its pitch rate and its pitch attitude. Okay, nose up or nose down. But it is a perturbation that generally is highly damped. So the aircraft recovers quickly from this type of perturbation. You can see that the damping ratio and the disturbances go to zero very quickly. Okay, so the angle of attack, the speed, the pitch rate, and the pitch angle all tend to go back to the equilibrium state in a fairly short time, less than 10 seconds. No, there are almost no oscillations here. The decay is almost exponential. Okay, there are no oscillations in the case of short period perturbation. You have oscillations for some state vectors here. In the case of physicoid, you have a change in pitch angle and velocity of the aircraft. Okay, so here you can clearly identify an oscillating mode with very light damping perturbation. In that case, there is an almost immediate stop in the perturbation. So after 2 seconds, 3 seconds, you're almost back to the nominal condition of zero. Okay. Any questions? Any other questions? Okay, so to summarize, when looking at the stability characteristics of an aircraft, we can identify 5 modes of stability. 2 modes in longitudinal direction, short period and fugoid, and 3 modes in the lateral directional directions. Roll damping, quickly damped, and then you have Dutch roll and spiral, which in this first case you have a highly sinusoidal behavior, lightly damped, which combines yaw and roll effects. And then you have spiral, which again combines roll and yaw perturbations, but on a much longer time scale. And while the Dutch roll is generally damped, even though it takes a long time, the spiral can be either stable or unstable. Okay, if there are no more questions. No? Yes. Oh, it's the lift. Because yes, because when you have a roll perturbation, so this is the unperturbed situation. And then you have change in the attitude. Okay, so in the case of roll, one wing goes up, the other wing goes down. Okay, so the perturbation is acting in this direction. Okay, now what happens to the lift in this case? You're a pilot, you should know what happens in this case. Which one? What do you mean you think? So you have an increase in lift here compared to here. Okay? So if you have an increase in lift on this wing, and we assume that the lift is applied, let's say, midway along the wing, you generate a moment that acts in this direction. Okay, so it pushes the aircraft, it pushes the wing back up. Okay, so that is why the roll damping is quickly eliminated by the aircraft. Yes, by the magnitude of the magnitude of the lift differential between the two wings. Okay, the greater this is, the greater the torque that you generate, the quicker the damping effects on the motion of the aircraft. Okay, so do this now.
없습니다. Cái hàng mấy quả. Rồi, rồi qua đời rồi.
has an answer? Okay, the first thing we can we can say is that the envelope of motion will be given by this equation here. Okay, the solution of which will be this form. Okay, lambda 1 and 2 are equal to a plus minus imaginary b. So we know that delta 1 is equal to 5 degrees and delta 2 is equal to 2.5. So we can take the ratio delta d1 over delta d2, and this will have to be equal to a d1 over a d2. Okay? And this we can write as e a d1 minus d2. Now we can get rid of the exponential term so that we have the logarithm of the ratio delta d1 over delta d2 is equal to a d1 minus d2. So the only unknown in this equation is a. Okay, so we find out that a is equal to 0.105. Okay. Tan, is this number correct? Yes. Why? And the number is correct. You sure? What does this tell us?
Exponential.
What does this equation tell us? This equation here represents the red line. Okay? The envelope of our perturbation. Clear? Yes. So, let me ask you again. Knowing that this represents the red line, is this correct? No. Yes or no? Make up your mind. Why not? Why not? Because? Sorry? Why? Because? Yes. So? Why does it have to be negative? Because going down. Okay. I would prefer more mathematical language, but essentially this is an exponential. Okay. So if the power of your exponential is positive, the exponential does like this. If it's negative, it does like this. Okay, so this should have a minus 0.105. Okay, so this is important because it is the first check that you can make that you are on the right track. If the stability, if the perturbation is stable, A has to be negative. If we had a perturbation like this, so this here is our envelope. In this case, the value of A would need to be positive. Okay? So if your perturbation is stable, A is negative. If the perturbation is positive, if the perturbation is unstable, A has to be positive. Okay? So this allows us to determine the value of A, and then the value of B is simply given by 2 pi divided by the oscillation period, T. In our case, T is T2 minus T1, that is 6.6 seconds. So we find 2 pi divided by 6.6 seconds, we find that B is equal to 0.958. Sorry, 52. So our lambda 1, lambda 2 are given by minus 0.105 plus minus I 0.952. Lambda is the solution of the characteristic equation here. Okay, where omega n is the natural frequency of the oscillation. This parameter here, C, is the damping factor of the oscillation. Okay? So the solution to this characteristic equation is our lambda 1 and lambda 2. Okay, so if we go back to this, here, lambda 1 and lambda 2 are the solution to this. There always is. Haven't you done this in dynamics and control? You should have done this already. In fact, you should have done it in dynamics, so first semester. Tell me you've done it. Yes. Okay. Tell me you forgot. Okay. Okay, so we have this equation here, and the solution can also be given by lambda minus lambda 1, lambda minus lambda 2 equal to 0. lambda square minus lambda lambda 2 minus lambda 1 plus lambda 1 lambda 2 equal to 0. Okay. So we can write this as lambda square minus lambda 2 plus lambda 1 plus lambda 1 lambda 2 equal to 0. Okay. So if we compare this equation with this one here, we see that lambda 1 and lambda 2, the product, lambda 1 times lambda 2 gives us the natural frequency. Okay, so we take this, we multiply it, so we will have 105, sorry, 0.105 squared. Okay, the other terms, the imaginary terms, cancel each other out. And then we have this term squared. So omega n is equal to 0.958 meters per second. Okay? And then we see that this term here, lambda 2 plus lambda 1, sorry, minus lambda 2 lambda 1 is equal to this term here, 2c omega n. Okay, so we find the value of omega n from this equation. We substitute it into here, and we find the value of the damping coefficient, C. So the damping coefficient is 0.11. Okay, so damping coefficient, undamped natural frequency of the motion. Sorry?
It's not use.
Okay. Any questions?
Then using it in the imaginary number. I never heard before.
那时候是 cancel 一下。
Yeah, so it's very perception. So I don't know how it So it's just two real number. Treat them as two real number.
Okay, next week, as I said, there are no classes for flight mechanics, so we'll start again on Monday 9, and we will go through the last tutorial, which is on Moodle. Now, there is an exercise similar to this in the tutorial. I think it's an unstable perturbation rather than a stable perturbation. So you will be able to determine the undamped natural frequency and the damping coefficient. So you would only stop here. However, in the question, there is a, let's say, a trick. to discover, okay, to get the correct answer. And I'm using the word trick, but I'm not trying to trick you. Because then I will explain
Oh, yes.
what the problem is. But when you're doing that exercise,
So this woman, right?
compare the situation that you have there with the situation that you have here, and see if you can come up with what the difference is and how you would deal with that difference. Okay? So I will see you in 10 days' time.
This.
This no, the other before that. Hey, how to do the form? Calculator, how to do the form? And that's it, equals.
Miss, you already see? Sound it right like that.
Correct.
No, without square.
Without.
But lambda 1, lambda 2 is
Oh my god, it's
square.
square. Oh, I got lag. Fuck.
Oh,
Oh, late by 15 minutes. Now lah, walao.
okay. See you later.
Yeah.
What time you all going? Straight after lab. By then I'll have to come back.
Okay lah.
Should be lah.
庄乐，你几点放啊？
Maybe. Huh? T14.
What do you use computer network? But then where you going?
I'm going home first.
Which home?
Real home. Yishun. I go back, take my stuff to go back to the fake home. Done.
Why not just do it tomorrow?
Cause I want to stay over tonight.
Yeah, I got nobody.
See you.